So the last session about Federica. We have 3 more speakers. First speaker is Joseph Pons from I2CAT, and he will speak about the IP sphere and Federica interoperability prototype. It's been developed by the joint research activity to Federica. I have to find the slides. Okay, so please.
Hello all, good afternoon. I will present a prototype for the interoperability between Federica slice and other IP domain by means of the IP sphere framework. This is the index that I will follow. First, the motivation that who has to make this presentation, the IP sphere solution or implementation about this prototype, and finally the deployment and validation and the SM child modules. Okay, as Mauro said in his presentation, the Federica goals is to create an infrastructure to allow the researchers to make experiments with full control of the resources that they own, and also to support on research in virtualization, and more concretely about multi-virtual domain control, management and monitoring, and virtual services and user-oriented control in federated environments. This is the Federica infrastructure. This infrastructure is composed by routers with logical capabilities, also with computers with some software for virtualization and or software for routing, and switches. This infrastructure is deployed over the GN2 and the NRN's substrate. And this physical infrastructure can be virtually partitioned, creating slices for the users. A slice can be shared or dedicated IP network, resources without any configuration, etc. Our new objective for Federica is, if we imagine, for example, a researcher who owns a Federica slice, he can own another slice as Jenny, for example, and he may want to join these slices, creating or merging them in another big one. But we can think how this is possible, and we can think that it's very easy. He can create this path through other network providers. But now we ask with other questions. How can negotiate and establish on-demand these paths? And after this establishment, can he manage and monitor them easily? The idea is to have a framework that offers us the mechanisms in order to establish these paths on demand, and after this establishment, this framework can interoperate with other modules in order to manage them. So that there is the IP sphere framework that allows this type of collaboration between providers. The IP sphere framework is property of the IP sphere forum. The IP sphere forum has become a member of the TMF, and this framework, as you can see in the picture, is allocated in between business and management over the control and management plane. So it is the appropriate framework in order to offer this type of mechanisms for collaborating between partners. As I said, from a standard organization, it follows the standards. I think it's something important, and there are some important features of this framework. The IPsphere framework has two roles. The first one is the element owner, that is a service provider who has some elements. An example, a transport provider offering IP transit. And the other role is the administrative owner. The administrative owner is in charge of orchestrating the different elements that the element owners provide in order to use them in order to create a bigger service and offer it to the customer. About the IPsphere components interactions, firstly, we have the element owner, as I have explained, and there is an element. What is an element? An element can be part, for example, of a connectivity path. In the context that I have explained before, an element can be a path between the two edge nodes of the Federica slice. This is an element. And this element is mapped to the software using templates. These templates can be created by the elements owners. We have to say also that these elements maps a service in the underlying management system. That can be the management system that manages the network the network who the element owner owns. The element owner controls the SMS child, and with this piece of software, we can create the elements offers that we publish them into the IPsphere registry. In this registry, the registry can be viewed by the customers in order to give the necessary elements offered by several element owners in order to create a customized service. This service is mapped using a service script. In this script, there are listed the several elements that conforms that. And finally, the SMS admin is the module that orchestrates this search. Once the search is finished, the service script is sent to the SMS parent, that is the module that uses the administrative owner in order to activate the service. For activating the service, the SMS parent creates an element order that is sent to each SMS child that owns the element that has been published earlier. Finally, the SMS child, when handles the request from the parent, sends the message to the underlying management system. In our context, we have two use cases. The first use case is that the researcher and the providers that are in the middle of the path has to publish their elements to the IPsphere registry in order to can be used after it. Here you can view as an element that is published in the registry maps a service in the management system, and in this service we can specify the several parameters as source and target IPs, the quality of service parameters as the bandwidth of the path, etc. And here you can see an example of the templates. The first one is a service template where there are listed the different elements with his identifiers, and under it there is an element template with, for example, the server IP and client IP address of the edges of the slice, and also the commit rate that is allowed for the path. The second use case is the activation or deactivation. This use case is triggered in this case in our context for the researcher, acting as an administrative owner, and he talks with the SMS admin software. This software invokes the SMS parent sending the script, and the SMS parent has to send a sequence of activation messages to the SMS child in order to activate the elements. Each SMS child can have a different management system under him. For example, one of the management systems can be Manticore, or another one could be the Juniper SRC. In this case, when the service is activated, the path who initially couldn't transmit any content through it, when the service is activated, then the content is transmitted correctly through the path. Here you can view the activation sequence. There are 5 messages for the activation. The 2 first messages are in order to set up the activation, sending the parameters needed for configuring the service, and in order to verify that the service is unactivated. The following 2 are for execute the activation, invoking the XMS system, and this software triggers the activation to the router. And finally, there is a message in order to assure that the service has been activated. For the deactivation, there is only a message that deactivates the service and returns the element at his initial state. For our prototype, we have implemented one of the modules of the IP sphere, that is the SM child. This module is implemented with modularity, so we have implemented several drivers in order to talk with the underlying management systems. The first management system that we have is the Manticore. Manticore IP service is a web service-based system that provides the ability to define and configure physical or logical IP networks. But we have the inconvenience that the software had to be enhanced in order to provide the capabilities needed for the IP sphere framework. So that we started using the Juniper SRC, that is a device, property of Juniper, that can provide this type of mechanisms. Our final objective is that the child publishes and activates elements from the I2CAT Federica slice, interoperating with the Manticore management system. And when these elements are activated, then some type of traffic is transmitted. Okay. Then we have deployed and validated the software using two scenarios. In the first phase, we used only the SRC instead the Manticore software, and we done the deployment using an interdomain testbed. This testbed is composed by our lab in I2CAD and also connected with a lab from another provider that also is in the TM forum, connected by a tunnel. This data plane is connected with an SRC, as I say, and this SRC is managed by the child. In the second phase, we used Manticore for one of the, well, we tried to simulate an environment where we had two different networks. Using an MS7 router from Juniper with logical capabilities, we simulated that we have two routers, and so that two networks in order to have a network, for example, as a Federica slice, and the other network acting as another service provider network. One of the networks was managed by the Manticore software, and the other one with the SRC. The final objective was also transmit traffic between the two edges of these networks once the service was activated. This test was done receiving the requests from an SMS parent simulator because we haven't any SMS parent component. Our design final scenario is the scenario that you have in the picture, is the data plane that I have explained before, but now our lab is connected to our Federica slice. In this slice is managed by Manticore, and the other slices can be managed by the SRC. This is a more global environment, and the result it will be to validate also the transmission of content traffic between an edge point of a machine, for example, of the other service provider, and a machine from a Federica slice. Here you can view more detailed what are the SM child modes. First of all, there are the SM parent simulator, who acts as a parent and involves the child. The SM child core handles the requests and sends it to the corresponding driver, and the driver talks with the corresponding management system. There is a persistence module in order to store the information needed by the SM child for storing the status of the elements. And also we have a publisher module in order to allow the publishing of the elements to the registry. Finally, as a conclusion, the prototype implementation gives to Federica researchers the mechanisms required for merging its slices with another slice from Federica or other similar infrastructures. And also, the SM child component of the IPsphere framework has been implemented in the scope of the Federica project. He can publish elements to the IPsphere registry. He handles the requests from the SMS parent activating the required elements, and also communicates with Manticore and the Juniper SRC for triggering the activation of the corresponding XML service. This software has been tested using the scenarios explained in the slides before, And finally, we propose for the definitive validation to showcase the interoperability of the child with some parent developed by another enterprise in order to test the really prototype. We also would like to showcase this software configuring a testbed composed by a content sphere field trial and the Federica slice elements. The content sphere field trial is the testbed used by the IP Sphere forum in order to test the implementations of the framework. And this is all. Thanks for your attention.
Yes, if I understood well your presentation, so you can, you demonstrated on the connection between US and Europe, okay, that slice. So you can also use this part of the software for connection, the, let's say, University of the Malaga with the University of Brno, let's say.
Yes, because this is only an example. The sphere is let's say, a framework, and so is adaptable at any slice, any management system. So it can be used for several slices and several software.
Yeah, but if we are real, so this is the demo which is done on your demo prepared in the I2CAD, not directly on the Federica infrastructure. And so there are some requests that some university in Greek want to communicate with the University of the Ireland, okay? And they want to use the Federica as a transport environment. So this is what you said. Okay, so Federica used to just connected the slice from slice. But it's not allowed, as I understood. Where is the Mauro and the Bjorn?
But in this case, we can talk as if, for example, this framework can be used also in order to connect two slices of Federica, for example.
Ah, okay.
A researcher can have two slices from Federica and can connect them using this framework, so that you say is possible.
Okay. Okay, thank you.
Yes.
Hi, I'm Gerben van Malensteen from SurfNet. Another question, maybe adjacent to the previous question. If I understood it correctly, everyone who is connected to this framework can interconnect with each other and build pods as much or many as they want to. But how is it when you want to connect to another domain where Federica has not been implemented? Is there any connector interface from the SMS parent component, or is that outside the scope of this project?
Sorry, if we have any connection to the SMS parent?
Yeah, as long as everyone is under control of the SMS parent component, there's no problem. I can see that. But when there are multiple domains, let's zoom out a little bit. Are there any inter-domain brokering systems your system can connect to?
Well, our system now is connected only to the I2CAD labs and the other lab from the other service provider. But in the future, I would like to connect, to deploy a machine over the Federica slides in order to manage the slides, and so using the Federica test.
Okay, thanks.
So my last question is, so I don't need the mic. So the last question is, when your software will be moved into the Federica substrate,
is I think that is a layer little superior than the Federica infrastructure, because is a set of mechanisms in order to provide connectivity between several, not only for Federica, it can be used for connecting several other IP domains. So it's not at the level of Federica. Well, if you have more questions, I can respond you by mail. If you want.
Okay, so thank you very much again. And our next speaker is Peter Schudin from KTH, and they will speak about the network virtualization based on the OpenFlow thing. Okay, just. Fix it because of the streaming, I guess.
Thank you.
Okay, so I can just start the slides for you. Please.
Okay, thank you. This is joint work with my colleague Marcus Hydell, sitting over there, Georgia Contesido and Kyriakos Sarifits, and it's called Network Virtualization Based on Flows. So what I'm going to do now is, I know that this is probably a room full of networking experts, but I'm still going to give you a short background on network virtualization and flows. And then I'm going to tell you a bit about OpenFlow, which is a relatively new concept. So I'm also going to go through a brief introduction to that, and then I'm going to come to the point where I talk about how are we using OpenFlow within Federica, and what are we doing with OpenFlow in the context of the Federica project right now. So, network virtualization, what is it about? Well, my interpretation is that it's about making a physical network appear as multiple virtual networks, but sharing, probably through slicing. You may or may not agree with this definition, but that is, that's my view for what we're trying to achieve through network virtualization. And it's about, in some sense, separation of functionality as well as traffic. We would like to keep applications, perhaps, on different virtual networks, banking, IPTV, web surfing, you name it. In a sense, separation of functionality on different slices, on different virtual networks. So what we're looking for is trying to achieve is a diversity of networking disciplines on the same shared infrastructure. We would like to share a network, we would like to use it for different things, use it for different ways, using different protocols. And in particular, what we are interested in within Federica is to enable network researchers to do experiments with new protocols, new services on a network infrastructure. Okay, so that's the first part about network virtualization. But there are some limitations now in what we actually can do in terms of virtual networks. Because the hardware that is out there doesn't really allow us to do perhaps all the things that we would like to do. The nodes, switches and routers are closed, in a sense. Which means that we, as researchers, as innovators, can't get access into the boxes and do our experiments with the inner parts of the boxes. We can't change or modify the basic behavior. We heard earlier today from Jean-Marc that there are some support, for instance, in Juniper routers for doing applications, for instance, implementing new routing protocols. But fundamentally, a virtual network is still an IP network or perhaps an Ethernet. But that is the kind of network service, network abstraction that we get through a virtual network. It's still basically an IP network. So that means that if we would like to do more radical research, we are confined to doing that in our computers, in the endpoints, in the end systems. And the network that we can use is perhaps through overlays, through peer-to-peer networks, maybe some sort of VPNs, provided based VPN and so on. That is what we're limited to. So there are certain limitations in network virtualization, and that is what we're looking at here, and this is what we're addressing in these activities. Trying to look beyond that, what we would like to do in the future in terms of network virtualization for research. Okay, so that's the first part. Second part is about flows. So what is a flow then? Well, you can see it, the way we see it here is it's something that you can use to represent and characterize traffic. You can describe traffic, saying all the traffic going to a particular website, all the traffic going between two subnets, all UDP traffic, all traffic going from Peter's computer, or whatever. And the way we do that is in terms of header patterns. You can think filter lists. So we specify a pattern of the packet headers, the protocol headers of the packet, and saying that all the packets that match this particular pattern belong to this flow. So it is, in a sense, a general way of describing traffic. I can describe all kinds of IP traffic, IP network traffic with this. It's not restricted to any particular protocols or particular applications. It's a general way of describing traffic in our networks. It is backwards compatible, and what I mean with that is that we can describe things like tunnelings. We can describe that through flows as in terms of flow. We can describe VLANs in terms of flow. We can set up a pattern that represents the traffic that goes over a particular tunnel. If it's an IP over IP tunnel, well, then can we describe it in terms of the contents of the protocol headers. So flows are backwards compatible, and we don't need to modify packets because packets, they belong to flows automatically, which means that you don't have to encapsulate them to put them into a particular flow. We don't have to decapsulate them to take them out from the flow. It's just a way of describing packets. They already belong to a flow. We don't need to encapsulate and decapsulate, which means that we don't have to do header operations, packet manipulations in a network. And similarly, we don't have to modify the endpoints. We don't have to modify computers in order to send packets on the flow or to receive packets on the flow, because that's what they do. Okay, so that was a quick introduction to virtual networks and to network virtualization and to flows. So what is OpenFlow then? Well, it's an initiative mainly from the US, from American universities. And it came up as an initiative to open up commercial networking hardware for experimentation. The problem was exactly the one I described a few minutes ago. I mean, we don't have access to the boxes. We can't do experiments inside the boxes. So that means that if we like to do networking experiments, well, we're basically limited to doing that on open source routers, which is a great tool. We can do many interesting things with open source routers, but they also have limitations. So this was an initiative that came up in order to be able to do experiments on real networks and promote innovation in networking. And what OpenFlow does is it gives us access to flow tables and switches. Okay? So what is a flow table then? Well, the starting point here is that most switches, routers, they have different types of tables that are supported in hardware. Typically TCAMs that you use for different kinds of lookups, access control lists, classification operations for quality of service, and those kind of things. And most of the switches have that in different ways. And if we can get access to those kind of tables inside switches and routers, it means that we can, from externally, that means that we have a way of actually influencing the packet forwarding behavior of the switches and the routers. And that is a starting point of OpenFlow. If we can get access to those tables somehow, externally, then we have a way of actually controlling the data plane in switches and routers. There is an OpenFlow switch consortium, which is a group mainly of American universities who are promoting this, who are developing the OpenFlow protocol. And perhaps the most important part, there is OpenFlow capable hardware available. Some vendors have put support for OpenFlow in the products. Juniper has that, Cisco has it, NEC, HP, and several others And that is one of the important parts of OpenFlow, that there are actually hardware available, and the vendors, to some extent, are supporting this. Okay. The main part, the center part of OpenFlow is the OpenFlow table. The OpenFlow table is a table that sits in switches and routers. And it has mainly three parts. It has a rule part, an action part, and a statistics part. And the rule part, well, that's our filter. It's a 10-tuple where you specify the switch port, which is an incoming port, the port where the packet came in. That's a switch port. And then there are the Ethernet Ethernet source address, Ethernet destination address, Ethernet type field, VLAN ID, IP source, IP destination, IP protocol, and port number, TCP or UDP. So the rest is your basic filter specification. And to this we can associate a mask, so it's a ternary, 10-tuple, which means that you can sort of put don't care values for different fields, which makes it possible to specify wildcards, prefixes, and so on. So that's the first part, the rule part. The second part is the action. And this is perhaps the really new thing. The action says that this is what the switch should do with the packet that matches this particular rule. The first action is forwarding. So when forward this packet to this port or this set of ports. It could be multiple ports in case of multicast traffic. So that's the first action, plain forwarding. And that means that we can actually control the forwarding switching behavior of the switch in this way. We can insert a rule which tells the switch to switch packets out to a specific port. All packets that match this particular flow should go out through that port. That's the first part. The second part is where I say that this is some sort of an exception packet. This is something that we need to act upon in the control plane. So when a packet matches this particular rule, and the action says encapsulate it forward to the controller, the switch is going to take that packet out of the data plane, encapsulate it in OpenFlow protocol format, and send it to a controller. And the controller is an external control process running somewhere, perhaps in a PC, outside the switch. So it's really an external process somewhere in the network. We're going to talk more about the controller in a short while. The third action is about dropping packets, acting as a firewall perhaps. And the fourth is send the packet to the normal processing pipeline. So what this means is that, well, this is really something that we're putting ahead, putting in front of the regular packet processing inside the switch. So when we say that send to normal processing pipeline, it means that we are going to take the packet and the router or the switch is going to do its regular processing. So if it's a router, well, then it's going to go through the IP forwarding loop. If it's a switch, then it's going to go through the regular Ethernet learning switching behavior. So this is something that we can sort of put in front of the regular processing machinery of the router or the switch to control what the switch is going to do. Okay? So that's the first part, the flow table. And another part that is important is the controller, because that is where all the intelligence is. That is where logic is. The controller has a secure connection to the switch, running on top of SSL. And the controller and the switch are exchanging messages, messages over the secure channel. So what could typically happen is that a packet comes in, it hits this rule in the flow table which says that this packet should be encapsulated and sent to the controller. Then the switch is going to do that, encapsulate it, send it with SSL to the controller. The controller is going to analyze the packet and say that, we probably need to set up a new flow rule in order to deal with this packet, perhaps. And then the controller is going to go back to the switch, set up some new flow table entries for that particular packet, and send the packet back to the switch again so it can run it through the regular machinery. And that gives us some sort of an on-demand behavior where the controller can react to the traffic that's happening on the switch and modify the open flow tables sitting in the switch depending on the traffic, for instance. There are mainly three kinds of messages inside OpenFlow, in the OpenFlow protocol. Controller to switch messages, that's the messages that the controller uses to set up things in the OpenFlow switch. It can configure the switch, set up entries in the flow table, and ask the switch about what kind of capabilities it has, for instance. Asynchronous messages go in the other direction from the OpenFlow switch to the controller. They can be things like events happening on a port, the port goes down, and that is going to generate an asynchronous message going back to the controller. And then the last type is symmetric messages, which are sort of diagnosis messages for making diagnosis of the connection between the controller and the OpenFlow switch. Okay, so those are sort of the three components of OpenFlow: the flow table definition with its 4 actions, the OpenFlow protocol, the messages going between the controller and OpenFlow switch, and the controller. So that is basic OpenFlow, and that is what OpenFlow is about so far. What we think is interesting about this is, well, for one thing is that in this design there's a model where we've taken the control part of the switch, and we put that in an external entity. We put it in a PC, in the controller. So it's really the controller where the control plane is sitting. The switch is just doing the data plane. So we've separated the control plane from the data plane. And the same controller can control many switches, which means that you can actually have a more centralized view of how you're operating around in the network. The controller, the central controller, is sitting with the full network view and can make decisions that are influencing many switches, many OpenFlow switches in the network. And that opens up a lot of interesting possibilities because there's a lot of flexibility in terms of making routing decisions, management policies, and so on. So this is one observation, that the OpenFlow protocol and OpenFlow itself sort of promotes a centralized model of control. Okay, so what are we doing in Federica then? Well, the yellow part is the question that we're asking ourselves now. Can we use OpenFlow as a basis for an open virtual network architecture with a powerful management interface and with efficient support in hardware? So what does that mean? Well, we're thinking here in terms of flow-based network virtualization. Can we build virtual networks based on flows? And can we elevate this so that we make the virtual networks based on OpenFlow as the sort of objects that we're operating on in terms of network management? Instead of don't care too much about low-level details, instead we're sort of working at a high level of abstraction and dealing with virtual networks where we use flows to describe the networks. And this is perhaps more of a long-term goal for this activity in Federica. As a more short-term goal, we are looking at OpenFlow as a tool for automatic configuration of virtual networks. We have the OpenFlow protocol that can set up flow tables and switches. So can we use that to make virtual network setup more automatic somehow? So the activities that we're having right now is that we're designing a virtual network layer on top of OpenFlow and designing a virtualization service interface so that we have an interface, a management interface that we can use to access this. And what are the key issues involved then? Well, first of all, we need to come up with a virtual network abstraction based on flows. What does this mean? How do we represent the virtual network in terms of flow, in terms of flows? That's the first part that we need to think about. And once we've decided on that, we need to come up with a way of provisioning virtual network, which means that we need to translate virtual network, the definition of virtual networks, and the things that we can do on virtual networks, the operations that we can do on virtual network to open flow protocol operations. And the last thing is we also need to think about access control, authorization, and validation, meaning that we need to have some sort of mechanism that controls who is allowed to do what on which virtual network, and so on. We need to have a way of resolving conflicts between virtual networks, because it could happen in theory that we're having flow descriptions that belong to more than one virtual network. So then we have a conflict, and then we need to have a way of dealing with that and resolving that kind of conflicts. So the way that we are representing virtual networks in OpenFlow is through two main parts. The first is that we say that the virtual network in an OpenFlow network is a sum of flows. So we define a virtual network as a set of flows. So many flows constitute a virtual network. So that's the first part. And that is the one thing that we need to specify in order to define an OpenFlow virtual network, a set of flows. And then for every OpenFlow network, a virtual network, there's going to be a set of functions. And the functions give us the flexibility and the possibility to do routing on a per network basis and make policy decisions on a per network basis. So we have a way of providing for every virtual network the routing functionality, the policy functionality, so that different networks can have different routing functions, different policy functions. And those are parts of the definitions of the virtual networks, those functions. They're probably going to be a set of built-in predefined functions, standard functions, but still that is something that you specify as part of the virtual network definitions. How do we do routing for this particular virtual network? How do we do policy functions? So whatever are the functions is that we like to make configurable for this virtual network. And then the controller is going to consult those virtual network definitions and set up the flow tables in the OpenFlow switches according to the routing functions and the policy functions. And this can actually happen in a number of different ways. The most common way in OpenFlow right now is to do this on demand. So it's traffic driven. So typically OpenFlow tables are empty initially, so when a packet comes in, it's going to trigger an event which activates the controller, and the controller decides what to do with this packet. And in that way, the tables are going to be set on an on-demand basis. But it could also be pre-configured, so the controller decides to set up the OpenFlow switches in advance. Both of those are perfectly possible, and you can even combine them if you want, somehow. So what is going to happen is that, say that we have two green computers in a network, and now we'd like to build a virtual network, an OpenFlow virtual network that connects these two computers to each other. Those are the only two nodes on this particular virtual network. So what's going to happen then is we're going to request a virtual network somehow from the virtualization controller, telling that, okay, this is what this virtual network looks like, these are the flows that belong to this virtual network, and this is the routing functions and the policy functions and so on. The virtualization controller is going to use the OpenFlow OpenFlow protocol to set up flow entries in the switches, according to the definition that we're given to the virtualization controller. And the result of that is going to be that we're going to set up a flow table entries through the switches that, in such a way that we're going to connect together these two computers with each other. Okay, so what are we doing? Well, right now we are doing design and implementation work. We are doing a virtual network controller, an implementation of virtual network controller. We're using, and the basis for that is something which is called a NOx platform. The NOx platform is something which is called a network operating system. That's the term that they're using for it. But it is a software platform for doing OpenFlow controllers. And it's an open platform where you can do plug-in modules, so that is what we're using as a basis for doing OpenFlow virtualization on top of this. We're doing this, the current state is we're doing a small-scale experimental study in our lab network. We're doing an open source software reference implementation of an OpenFlow switch running in Linux. So that is the current status. What we're looking for doing in the future is to do a more large-scale experimental evaluation, perhaps in the Federica infrastructure on OpenFlow-enabled equipment. Okay, so to conclude this project is about network virtualization based on flows. And we're looking at this to see if flow-based virtual network could be a suitable way of dealing with networks in general and doing network management in particular in the future. And we're doing this with OpenFlow. And the main point about OpenFlow is that it's something that actually has hardware support. It's a way of getting access to the hardware in our networks. And we're looking at this as a virtualization mechanism for Federica. And there are two parts to that, the OpenFlow virtual network definition. And the second part is management for flow-based virtual networks. And we're currently working on design and evaluation of this. Okay. Questions?
It's about the authentication, authorization features of the protocol. Thinking about, in a virtualized environment, how do you transfer the user rights down to from the OpenFlow controller down to the measurement points?
This function has to be, the controller has all the intelligence, and the controller is the one who is in charge of doing all the access controls and maintaining all the policies. So all that has to be in the controller.
So once you access the controller has full control. You don't, okay. So the access to the controller is not under OpenFlow protocol. It's something that you can do as, I mean, requesting some operation at the controller.
Sorry, I can't hear.
When you are going to request the controller to do some operation, you're not using the OpenFlow protocol.
No, how you're accessing the controller, that's through other mechanisms. You can, it's
Web
a configuration
or
of the interface. It's a user interface to the controller, and that is not the OpenFlow protocol.
Mm-hmm. Okay.
Thanks for the presentation. I've been reading a bit about OpenFlow lately. I'd like to understand, are you doing this experimentation in the laboratory, or are you already moving this to a large-scale network?
Right now
I understand
we're
that you have to have the hardware for OpenFlow together with the switch hardware.
Right now we're working on the functional level. We're doing it in a lab environment, and we're doing it on an software-based switch. So that is what we're working with. We're looking to get some hardware for this that we can do some more experiments with. But right now it's in software.
There is information that McKeown is talking to lots of switch manufacturers to put this hardware on their switches. You're not a...
Yes, I mean, it is available. I'm very unsure about the commercial status, but it is available in some vendors' products. So Juniper have it, Cisco have it, HP, as I said, NEC, some others. Yeah.
Thank you.
So,
I have a question. So, as I understood from the answer to previous question, you are doing it in the parallel compared to Federica infrastructure. Mm-hmm. So it's another way how to create the links in between the Federica nodes. Mm-hmm. Not via Manticore, but via this technique, more or less. And so do you have some idea or the perspective how, if you can somehow use the slice for using this as a tool for making the virtualization in virtualization, I would say. Because what Federica current can give you is they just slice, as I understood. So I'm not sure if you can do this on the virtual routers which are virtual in the slice. So this is my question.
Well, virtualization is tricky, in particular virtualization on top of virtualization, but I would say no, because the abstraction that you get today is still virtual routers. It's not open flow switches, it's not open flow network, it's still virtual routers. So this functionality is not there now. So I would say no.
I think the bottom line is that this is a completely different approach, virtualization approach that we are currently using in Federica.
I mean, to put this into perspective, I mean, this is a research activity, so it's not, the main goal is not to deploy this within the limited time frame of the Federica project. I mean, if we can, it would be good, but that is not really the main goal here. The goal here is to do research on.
My question was, because in Federica we are looking at advanced users. So if you can be the advanced user for the Federica platform.
Yes, maybe. Yeah, maybe. Okay, thank you.
Thank you very much again. And our last speaker, Eugene Novotny from CESNET, and he will speak about the NetFlow-based traffic monitoring in the Federica project. So please.
Okay, thank you. I will talk a little bit about network-based monitoring, flow-based monitoring for Federica project. In the previous presentation, just before the lunch, Jiří Navrátil talked about the SNMP for the flow for the monitoring of Federica network, and it's not necessary to be said that there are two kinds of the monitoring. One kind of monitoring is based on SNMP, it's a host-based monitoring, as second is monitoring based on flows. I will compare both approaches in the first presentation, and after that I will talk a little bit more about the traffic measurement and flow-based monitoring. Okay, so what are the goals for traffic network monitoring? We would like to observe all flows in the networks, and we would like to see statistics about the VLANs, protocol services, and so on. One of things what we can be done with this project is discover network structure, and I will use it later on as the test case for the monitoring. So first, SNMP traffic monitoring is a standard approach. It's based on network devices. The network devices has SNMP statistics, and we can read the SNMP statistic, and we can monitor them. But the issue is that we have no knowledge about the source and destination IP addresses, type of traffic and protocols, and so on. Here we can see the example of SNMP output. The traffic monitoring based on NetFlow is a little bit different. There was in previous presentation something about the NetFlows, so I would just say basic principles. Flows is communication between two hosts, and flows is defined by source destination port, source destination IP address, and protocol number. And we observe flight time, we observe number of packets, sum of bytes, TCP flex, and others. So we can see here how looks output from the such system. Let's compare both approaches. SNMP is well known, is built almost in all network devices, but has a limited level of information. NetFlow is built either in high-end routers or in dedicated monitoring probes like Flowmon probes, NTOPes, F probes, and others. But the benefit is that we have detailed information about the packets, and we can use it for advanced network traffic analysis and measurement. So we can have much precise results with using NetFlow monitoring. So how it could work in Federica network? We know that Federica network is based from the hardware level. There are right now four basic points in the Federica network, and on top of the hardware there are virtual slices. Virtual slices use VLANs for the communication between the slices. So we use 802.1q VLAN tags, and that way we can share one physical lane with several virtual lanes. So we need to add VLAN information to flow record. The issue is that in standard NetFlow protocol V5 and V9, there is no definition for VLAN. So we need to solve that issue. The solution is to use dedicated Flowmon probes with kind of VLAN support. Because as we can see, NetFlow version 5 doesn't support VLAN tags. Version 9 defines VLAN tag, but routers and probe doesn't support VLAN export, and collectors doesn't support VLAN handling. In our case, we use special Flowmon probes, which was tuned to to have VLAN support, and we tune the NFSN collector, what we use as the collector to be able to work with the VLAN. We use the DST AS field for this. So that way we can monitor the VLAN tags. How it works? So it's the basic system, and we will deliver probes to each node, and data from the probes will go in the data analysis centrum, where we can do other processing. Right now, it's delivered just one probe in Prague, and it's in the test regime. So, how looks the one node? We have node here in Prague, and there are 4 lanes, and on each lane is optical or RJ45 tap, and information goes into Flowmon probe 8000. It's an 8-port flow monitoring probe. There is the block structure of the NetFlow monitoring system. Here is the Flowmon probe, which take data from the network, and here is configuration center, which is used for the configuration probe. And on right side, you can see data analysis center, which is based on an NFSN collector, and you can control probe from this data analysis center, and back you can get information from the probe and analyze them. The Flowmon probe is based on one output of the GEAM2 project, is based on security toolset, which is the combination of Flowmon and NFSN. So, data analyzing center catch data from the Flowmon probes, stored them, and it's, as I said, it's based on NFSN and NFDump tools. What we can do in traffic on the data center, we can correlate data from various probes, we can do data reconstruction, we can work with link behavior estimation, and so on and so on. And of course, users can interact with the data center. So it's the information, so user can read information from the data, from the network traffic network data analysis center. Okay, so what we can have as the statistic, we can have raw, NetFlow, 5 and V9 data, we can have top-end statistic, we can see top-end users and so on, and we can also filter data according IP addresses, protocols, and VLANs. Especially important is to be able to to filter data according VLANs, because we can see traffic in one slice. We can do also flow aggregation, and we can work with VLAN tags and interface numbers. So let's go in the one use case. How could be probe used for the estimating of data paths? We know that in Frederica we have a real infrastructure, but we would like to test, for example, new protocols. There was discussion about the open flow protocols, for example. So if we want to, if there are data coming, for example, from Cessnet to Poznań, it could go this way, because the virtual slice or data in the virtual slice can go other way than the physical and on the physical level. So it can go this way or that way, that way or that way. So we can have 4 passes, and we would like to discover what path is right in the slice. So here we have information from the probes, and what is important, we have information. We can see how the flows go through the nodes. So we see ports. We have information in the data flows about the ports, so we can trace the data paths this way.
These are real flows, not virtual flows.
Please?
This refers to real.
It's a real flows in the slice, because we use.
The slice, is it
Slice use VLANs, so we trace the flows in the slice using the VLANs. Because yeah, we can isolate them, and with knowing on number of the port, we can trace the path. But this approach, it has some disadvantages, because traditional approach, it's for a long time path, but the structure of network can change time to time, and classical approach with, say, coarse grain flows cannot follow the change of the structure of the network. So we propose to use something what we named special purpose fine grain flows, which is just consists of one particular packet which is injected in the network, and we can trace that packet in the network, and that way we can discover paths much precisely and much faster than with this approach. So how it does work? In phase 1, we inject packet into network, and packets coming through the network, and probes send information that they find the special packet to data analysis center, and in data analysis center we put all information together, and we can trace the path very simply. So it's one of using of probes for the data path estimation. It could be very useful for testing of new protocols, for new methods, for new algorithms, and so on. So, so now some information about current system deployment in Federica network. Right now is deployed one probe in Prague, and we use that probe to monitor slice M with Prague, Milano, and Erlangen. It works on 3 VLANs, and we can also see the management VLAN. So it's what is done right now, and we have information from flows and from traffic in this initial slice. So, conclusion and future work. The proposed system is able to deliver detailed traffic information, not just information from the devices, but also for monitoring, and we can observe packets strewing through the network. Use tools support NetFlow with full VLAN processing, and right now NetFlow data are manually processed by operators. So it's the status for today. For next research, we need to deploy another probes to another nodes, so at least to 3 other nodes. And next work from outside would be to extend the functionality of data analysis centrum. So we would like to implement the algorithm for data path correlation. So we would like to don't do the work manually, but have some tools for data path algorithm. And we propose build this algorithm like plug-in to the NFSN, because NFSN is a very open tool, and we can simply plug some functionality in. And what will be another work for future, but it's for not for far, it's for far future. Implement precise timestamps, because if we would like to have more information, we need to have time correlation between the probes. Should be work not just on a NetFlow v9, but we should use also IPFix extension, and it could help us to improve data path reconstruction, because we know the precise time when the packets was observed. And also we propose to work on active network probes. So would be very interesting to have possibility to inject packets into network and see how they move in the network. So it's all for today. Thank you for your attention.
Questions about the monitoring?
Follow up on what I asked before. I mean, you assume here that all packets belonging to a slice will be tagged with a specific VLAN number and all that. Who is going to do that?
When you build a slice, you give the resources to the user which want to use the slice. The resources are processor power, memory in a VMware, and you need to give the user also infrastructure. It means some kind of network. So administrator of Federica give to user the processor power, memory, and network is because we have just one lane between 2 nodes. So network for the network we use there are used VLAN. So it's done by a network operator, a Federica operator.
Once we want to get beyond VLANs and you try different types of protocols, LSPs or whatever. So you're not going to have exactly VLAN types again.
No. Okay.
Yeah, I will try to answer this question, because I had the same, I had the slides in my presentation, which I show the results of the monitoring via this, okay? So there is a distribution on VLAN, and inside the VLAN, you can see the type of traffic,
yes.
SNMP or the other type of traffic, UDP, TCP, and all other stuff, and you can see even more. Okay, and but the most important is that in the VLAN, which we are using for connection between the nodes, you are losing totally information about the direction of the traffic, because you can see the. So if the traffic is simple and if the network is simple, so you easily can distinguish from where to where the traffic is coming. But if the network would be the full implemented, that means you will have a traffic from, let's say, from Sweden to the Portuguese, to the Portugal. Okay, so you will not know where traffic, how traffic is going on, because there is no the trace route. There is no trace route because it's everything masked is via tunnel, which is called a VLAN. Okay, so the VLAN you will see. Okay, so it goes from the Stockholm, and on other side you will see the end side, but you will not see anything else because everything is masked. But via probes, which you will have in the critical points, you will see, okay, this traffic belongs to this traffic. So, and especially if the traffic will be high, in the current situation, I had also the picture that if one peak appear on the interface in Prague, another same peak appeared in the Erlangen, so it was clear that this peak belonged to this peak. But if the traffic would be the high and your activity as a user will not be high and it will not create any type of peak, so you have to find it somehow. And this is only way how you can find out this traffic. So if you want to give some tool to the users which can trace their traffic, so you have to give him something like this. So this is...
Maybe we should say that the VLAN is another information in the header of the packet. So it's another information in normal physical structure is used for some purposes, but in Federica we would like to use VLANs to build cables in a cable, something like that. And with that probe we can filter information and we can see just that virtual cable. It's the main benefit of this approach.
Yeah, I think that this highlights very well the fact that when you virtualize and have different layers, then you do not really know the information which might be in another layer. For example, if you were able to just look at the configuration of the switches, obviously the switch contains the configuration of where the VLANs are and where are the directions, but the user can't access it. So for me, is more than just monitoring, is how to make a certain set of information available to the different layers in a way that is useful. This is my comment, at least.
Yeah.
So I believe that they will work on this in that sense that everything will be done by them. Okay? Everything will be done by them, but it will be exposed into the website or somewhere, just according to the rules. Okay, you are using the slice number 1, so you get the information about the slice number 1 and something more. Okay, yeah. And we can discuss what does it mean, that something more. And the users from the slice number 7 will get the information from number 7 and something more. Okay, yeah. What would be necessary.
Thank you very much again. And thank all of you for your patience, and all the Federica partners will be around, so you can just some questions if you have more. Thank you very much.